video capture all four boards, or should you stay in the middle?
I don't know. Probably
Yeah,
all
yeah,
four.
control.
Yeah.
They're pretty good. They can pan it.
But is somebody doing that? Who has control?
Yeah.
They normally do.
He's in
Turn the
there.
mic on, mate.
Oh, okay. Okay, thank you. And you can get all four boards?
Yeah.
Okay. Okay, so thank you for coming. This is the third time some of you are going to hear this talk, so sorry to bore you.
We came back.
You came back.
Aren't you even saying anything?
A few new things at the end. So I gave the first version of this to the Pauli Institute, and then at the Max Planck Institute, and now the Newton Institute. So we've got three good physicists.
It's an institutional thought.
Yes.
Going back.
So this is going to be on the topic of gyrokinetics. We'll be looking at fluctuations in gyrokinetics and looking at statistical absolute equilibrium, or what is sometimes just called absolute equilibrium. But in fusion, we would think of MHD equilibria, so I'm going to emphasize the statistical absolute equilibrium. This is work I've done with a postdoc, Zhenzhou Zhu, and myself. And one new thing is that the paper is finished, so if anybody wants, we've submitted it. If anybody wants a copy, send me an email, Hammett at pppl.gov, and I'll send you a copy of the, or point you to where the paper is. Okay, so here's the setup. Here's the Gedanken experiment of what we're going to do. Let's consider a case where we've got a spectral gyrokinetic code, continuum code like GS2 or another one. And you can, one of the nice things about spectral codes instead is that you can turn off all numerical dissipation. So you can make them conservative. And we're going to, let's make this log of k. We're going to set it up so we have a certain range of k's that we resolve. So here's k max. And let's plot the energy spectrum of fluctuations on a log scale. And we can initialize, say, a bunch of turbulence at some initial point. And then we can let the modes nonlinearly interact in our gyrokinetic code. And we intuitively know that there will be scattering, nonlinear, there are nonlinear terms in the gyrokinetic equation, so there will be scattering between these modes. And over the long time, we kind of expect this to relax to some spectrum. And the question is, what is the final shape? Does it look like that? Does it look like this? Does it look like that? And one of the amazing things is that there is a tractable answer. This is first shown by T.D. Lee and others worked on this problem. Creation and Montgomery. Onsonger actually worked on early aspects of this problem in the context of fluid dynamics. Not in gyrokinetics. But the fact that there's this tractable analytic answer even in fluids is pretty amazing.
So you drive at that K, or that's just the initial?
This is just the initial.
Okay.
So I'm going to do non-decaying, right, there's no dissipation, and just looking at what the resulting spectrum is.
Right.
Yeah. So it is somewhat artificial. The real world, I think, is more driven dissipative turbulence, and there you get the inertial range and cascade to dissipative range. Yeah. And I think that there are two main motivations for pursuing this, even though it is idealized, even though we've turned off dissipation and it's not driven. One is that it just gives us, I think, some insight into the nonlinear dynamics, and it can tell us things about whether there's a forward cascade or an inverse cascade. And so in the early days, they found significant differences between 3D and 2D. I think the other main application is as an exact nonlinear benchmark, analytic benchmark for codes. So it's a nice nonlinear case that codes can try to reproduce. So it would be interesting to see how gyrokinetic codes reproduce this. So the results for hydro were that in 3D, you find that E of k, which is normalized so that the total energy is equal to integral dk E of k, that this goes like k squared. That's the equilibrium spectrum in 3D. And this is basically equipartition of energy. So this would be proportional to integral dk k squared times the Fourier coefficients for velocity squared. So it's essentially equipartition of the energy among Fourier modes. Okay? And in 2D, the amazing, well, an interesting result is that you can get more complicated types of spectra that are generally of this form, to remind you. And yes, please stop me many times. It's going to be more fruitful to ask questions as we go along. So alpha and beta are generalized temperature coefficients, and they are set by initial conditions, by the amount of energy and entropy. And you basically get these more complicated spectra because there are now two invariants, energy and entropy. And this gives rise to the possibility of inverse cascades. And in particular, you often find for typical, if you initialize in the middle of your box the energy somewhere, you often find that the resulting spectrum has alpha negative, so that the spectrum looks like this. It peaks at the lowest k's. This combination is always positive, but as k gets smaller, the negative alpha causes a near, well, depending on how negative alpha is, can cause a near singularity at k equals k min, so that you get a large enhancement of the spectrum down there. Okay.
There's an implicit assumption of a large number of modes or a mixing property or something.
Yes.
Is that right?
Yes. Yes. Right. In doing this, there are a few ways in which that assumption arises. One is, the more trivial, is that you're approximating some discrete k sums as continuous integrals sometimes, but that's not essential, and you can formulate everything as a discrete summations instead of integrals. But the more fundamental is using a canonical equilibrium instead of a microcanonical distribution, which, well, that's one aspect. The other is an implicit ergodic hypothesis that there is mixing them, and which is easier to do if you've got many modes. Okay, so that's the motivation for this. And the other motivation is that there's this big difference between 3D and 2D. In 3D, you have one invariant, you get a spectrum that peaks at high k. In 2D, you have two invariants, you get a spectrum that usually peaks at low k. There's a range of possibilities, but usually peaks at low k. And the question is, what happens in gyrokinetics where there are actually many invariants, not just two? And so I want to go through a very simple limit of 2D gyrokinetics, and we will talk about that. So I'll be dealing with the gyrokinetic equation in a very simple limit. I could change everything and write it in terms of f, which is what I'm actually used to doing. But so we're going to be following the dynamics of the gyrocenter distribution function at a given position x. It depends on the perpendicular gyration velocity of particles, plus a Poisson bracket of phi bar, which is depends on position, and v perp in time, and g. Okay, so this is the phi would be the electrostatic potential, and phi bar is the gyro average electrostatic potential. which then depends on velocity because different particles have different gyro orbits, and so sample different parts of phi.
So let's see, is there a distinction between G and F?
No, not here.
And you write V perp instead of mu because,
Yeah, this could be, whoops.
I mean, I guess strictly in equilibrium, you don't have any varying V, right? So
I don't have any,
spatially varying V.
right. So
that's also equivalent.
right. I'm doing a simple slab limit where V is uniform. I haven't thought about. One could, I think, imagine what is the equilibrium limit in a varying V given by external fields, but we're going to do the simple slab limit here.
Can you tell us the relation between phi and G before?
Yes. So in K space, phi of K is going to be essentially proportional to integral okay. But then there are some coefficients up front. There are some an adiabatic electron response and a I might be writing too small, might I? So my scales are normalized to the gyro radius, so K perp, this is really K perp rho here. Okay. So this is the usual adiabatic ion shielding term, and this we can have some flexibility for what tau is. Usually we just set tau to 1, but this would be the electron to ion temperature ratio, and or for zonal flows we would set this to 0. I'm going to neglect that subtlety right now and just take tau to be a constant, but in general it can depend on K. Okay, so those are the two equations. That's a closed set of equations. This advances G once we know phi, and we determine phi by solving the Gyrokinetic Poisson equation. And I'm ignoring parallel dynamics. This is the 2D limit. Okay. And we're going to discretize this. And so this is going to be some coefficient. This whole quantity is beta k. And this velocity integral I'm going to write as a sum over n velocity grid points with a grid space. In a simple discretization, this would be the spacing of the ith grid cell v sub I.
This is state 5.
Sorry, what?
Are you still writing 5?
Yeah. This is all for phi. Of what? K perp v sub I times G of wave number k, velocity I, that can depend on time t. Okay. And let's see. The Poisson bracket. Yeah, I should remember to say this. We're considering particles that have a fast gyration and a slow drift. So the slow drift is the E cross B drift, and the fast gyration is V perp. And the E cross B drift is this term. So the Poisson bracket, you'll recall, can be written in various ways. But that's one way to write it.
Cross.
Yeah.
Yeah. Okay. And so one way to write it is like this. Okay. And just to be careful, this quantity here, I'm going to be calling later a weight for the ith velocity grid point, which can depend on k. There's a k dependence in here, and then the weights incorporate that factor and that factor. So when we sum them up, we get the density that needs to go into calculating the potential.
What's y?
What's y?
Okay, you're doing.
Okay, so
you're doing it Cartesian.
I'm doing a Cartesian slab.
You didn't write. I guess that's a vector x up there.
Yeah, okay. So, yeah, so the magnetic field is out of the board in the z direction. And so this z cross grad phi is this stuff. Okay. So now, if we Fourier transform this, our main Gyrokinetic equation, then the result is the following. We Fourier transform and look at the ith velocity grid point. V is just a parameter in the equation, so it appears there. And then we know that when we Fourier transform a nonlinear term like this, that we will get convolutions. And so I'm going to sum over all modes P and Q such that P plus Q are equal to the K that we're looking at. This becomes Z dotted with P will be the Fourier transform of that. Q will be this. This will be dotted with P cross Q times so phi bar. I should have written out what phi bar is, because phi bar is not the same thing as phi. But in Fourier space, phi bar is J naught times the perpendicular wave number times the ith velocity times phi p, which can depend on time, times g at Fourier mode q and velocity I. Okay. This is the Fourier representation of the Gyro averaging operator. Okay. Any questions about that? I should. Everybody's notation is different.
What's the I subscript?
Okay, right here.
Oh,
So
I see.
I discretized velocity space, and so I'm summing over n. And this is actually an important but subtle point. Just like we have discretized real space when we do a discrete Fourier transform and do a sum over k modes. And furthermore, we're truncating in k. We're not keeping an infinite range of k. So that truncation in real space is actually has a significant impact on the ability to calculate, or how one thinks about absolute equilibrium. Likewise, we're truncating in velocity space with a finite number of modes in velocity space with this discrete representation. In general, you could think of it, well, you can think of this as just a midpoint rule for this integral. There are more fancy integration methods where these weights, where the location and value of these weights are chosen to be equivalent to a high order Gaussian integration rule. But for our purposes, you can just think of this as simple midpoint integration. Beta of k is this factor here. I don't know if I can.
It had something to do with the beta of the spectrum.
No. So this beta of k is different than that 2D, yeah, sorry. Yeah, confusing notation.
When you said you were truncating in k space as well, that's implicitly built into the sum on k?
Right, right.
The p and q values?
So this p and q will only be over a finite range of k's. Over all p's and q's in my set that I'm containing that add up to that k.
So usually in the k-space truncation, there are issues about what domain you use to truncate it in order to keep the conservation laws. Do you have any issues in velocity space as to how you do that truncation?
Yeah. So in K-space, if I have a set of modes, and we're just going to use a square domain in K-space. And so as long as I sum over all modes in my domain, all possible P's and Q's in my domain that sum up to this K, this convolution will conserve the quadratic invariance exactly.
He means the alias.
Well,
Well,
actually,
so that's if you explicitly do the convolution that handles the de-aliasing issues. You would de-alias if you're going to do a pseudo-spectral method where you Fourier transform this to real space, Fourier transform that to real space,
Okay, sorry.
and then do the multiplication in real space and Fourier transform back. That's when you de-alias. But in a spectral approach, it's conservative with the convolution.
V.
And V, there isn't a problem. The conservation laws continue. They just get indexed by an additional parameter, which is the velocity. So let me talk about that for a minute. Yeah, and so we're just doing notation, getting the problem set up now. But if we go back to that equation, or with this replacement, we can multiply this equation by G. Let's write that out a slightly different way. Minus this, that thing. That's 5 bar G. If I multiply both sides by G, this becomes, of course, d by dt of 1/2 G squared, which is still a function of x v perp in time. And this becomes similarly just that. And this can also be rewritten as a minus the divergence of z hat. Let's see, how does this work again? Yeah. Z hat cross grad phi times 1/2 G squared. So if I integrate over all space and assume periodic boundary conditions, that vanishes, and so 1/2 G squared integrated over all space is a conserved quantity. And so I will call that G of V. And yeah, I'm going to average over the volume integral d2x of 1/2 G squared, which is a function of x and v perp. And in general, this is a function of time, but once we integrate over, it's a conserved quantity, so that is no longer depends on time. And in Fourier space, we can write this as sum over all k modes of G sub k. Well, I write this in various ways. Okay. And what's of interest is that this is a conserved quantity at every value of v. Right. All I did was integrate over x, and so this still depends on v. And so at every value of v, I have a different quadratic invariant here. So in principle, if I discretize into n velocity grid points, I have n conserved quantities. And instead of just the 2 of hydrodynamics, and the question is, how does that impact the spectrum? There is another invariant, which is the, goes by various names. But this is an energy-like invariant. And I'm not going to go through to bother calculating it right now. to prove it, but it's this is the invariant. You just have to do a few more steps, and it's been shown many times in various places. But if I substitute in for phi here, phi is this expression, then I can write it like this: pi sum over k modes. So there's a phi k squared here, so I'm going to be multiplying by beta squared. One of those betas will cancel this, so I get a beta of k. And then I'm getting a sum over all i's of wi times g of I. One of them will be complex conjugate. So there will be a sum over all i's wi g of k at the ith velocity, complex conjugate times the sum over all j's of w sub j. And I should perhaps point out that these depend on k, or as does that, times g sub k for velocity g.
Do these infinite capital G invariants have anything to do with Casimir invariants?
So these are quadratic invariants, and usually one refers to the Casimir invariance as the higher order than second order.
No, not necessarily, no.
Okay. So in general, any function, I instead of doing this, I could have multiplied by any function f prime of g, where f prime is the derivative of f with respect to g, and gotten that it's d by dt of f of g for any function f of g. So instead of just squared, it could be any power or any arbitrary function. So yes, they're related. But one of the interesting things is that spectral methods will conserve the quadratic nonlinearities, but they do not, as they're normally implemented, they do not implement higher order than second order nonlinearities. And so that's an interesting question. Can you alter the form of the convolution to, in some sense, de-alias for higher order nonlinearities and preserve a cubic and a fourth order Casimir invariant?
What is the argument that's given in the case of 2D turbulence? Because you could do the same thing, any function of vorticity.
Uh-huh.
So what is the argument that results in only quadratic vorticity squared being conserved?
Right, so any function of vorticity is conserved in 2D hydro as long as you keep full discretization. But once you truncate, if you keep only a finite number of k modes, then in 2D hydro you also lose the higher order invariant.
And is that the argument that the original proposers of the inverse cascade, they appealed to a truncation in k-space argument? They just said we like quadratic invariance.
They say at least this preserves the quadratic invariance. We would like to preserve others, but we don't know how. So this at least preserves quadratic invariance. And let's see what the resulting spectrum is.
Well, I mean, there's two different aspects of the problem. One, the absolute equilibrium, and two, the force dissipating version. I don't know that the people that did the inverse cascade in the force dissipated case talked about higher order invariance or not, but I guess I think in the absolute equilibrium case, fundamentally they build it out of a two-parameter Gibbs ensemble, and you wouldn't, in this case, write down a higher parameter Gibbs ensemble because those things aren't actually conserved under the truncation, as Greg said.
In the Taylor relaxation problem, there's a similar thing in that A dot B for any flux tube is conserved. It's argued that somehow the whole integral is better conserved than when you add some small units to
Right, I think the argument has a little bit of a different flavor in this case, but Greg is the expert here.
Sometimes people do appeal to more detailed arguments, that there are multiple conservation conserved quantities. Some are conserved better than others because of dissipation.
You don't have dissipation. You don't have dissipation.
But right. We don't have dissipation at all here. But some of the 2D Euler would focus on just energy, because they say entropy cascades to high K would be dissipated. There are a couple of subtle issues here. I guess I'm not going to go into more detail right now. But while we're talking about Casimirs, I'll just make a couple of comments.
I didn't fully. In my understanding of what a Casimir is something that's conserved by a Poisson bracket in a field theoretic derivation of the equation, independent of whether the Hamiltonian functional is conserved. I mean, you haven't actually written this in that kind of a form, so I'm not clear what the actual definition of Casimir is.
But these are things that are conserved by Poisson bracket.
What?
These are things
Oh,
that are conserved.
no. Well,
These are exactly the things.
it's a different kind of Poisson bracket that's used in the.
Well,
Oh, this is
the one with goals.
This is pretty much a standard Poisson bracket.
There's a field theory one where you're
Yeah.
taking functional derivatives.
Yeah.
That's what he's talking
Yeah. Okay. I have seen papers that refer to the Casimir invariance of this equation, where that's the Poisson bracket, and because you can multiply by any arbitrary function and integrate it there or integrate it there, you get.
Okay, all right, that's fine.
Why is it important for us to know whether these are called Casimir invariants? I mean, we're fairly confident that we've got the invariance of the equation, right? So
Yeah, these are the quadratic invariants, but there could, in principle, and so I'm going to look at how the dynamics are constrained by quadratic invariants. We've thrown away higher order invariants.
yeah.
And a possible interesting question is what happens, what is the effect of those higher order invariants?
It's worked before, it'll work this time.
Yeah, so there are some suggestions. Polyakov has suggested that higher order Casimirs will cause cascade that they cause that they keep the cascade to low K, to long wavelengths. However, there's a paper by Eying, not exactly sure how to say his name,
about.
and he claims that the Casimirs, just like in 2D turbulence, you can talk about energy and entropy cascading in opposite directions. You can ask, how did the Casimir invariants cascade in K-space? And Polyakov claimed that, or what is the word I use? Suggested that they cascade to long wavelengths. And Eying suggested they will cascade to high K. And Bowman has a paper last year in which he thinks that the G to the fourth moment, he was doing 2D entropy, but 2D hydrodynamics, so this would be the vorticity. He thinks that this cascades to high K, but the cubic has no preferred direction in K-space. There was no systematic cascade. Anyway, that's an interesting topic too that could be considered later.
Just to be clear, it's unrelated to the calculation you're doing here, right?
Yes.
Because you're doing truncated Fourier space.
Right. There are modifications to these kind of convolutions that can preserve higher order invariants. So one could conceive of investigating some of these issues, but the way we've truncated, it's only the quadratic invariance. Okay. Now I gotta go back. Okay. So, back with this equation. If we know g of k and I at some time, if we know the Fourier amplitudes at each wave number and at each gyration velocity vi, then we know the state of the system. So I'm going to consider, I'm going to define, let's see, yeah, I'm going to define a g, a vector g, which will be the set of all the Fourier coefficients for mode k at velocity I. And now I'm going to consider that to be a phase space vector. I can consider preparing a bunch of different systems with some initial conditions, some range of initial conditions. So I can prepare an ensemble of such systems and watch how they evolve in time. And I can ask, what is the probability of seeing systems with a certain value of g at a certain time t. Okay. So
G here is complex, or is it?
Yes, it would be the real and imaginary parts of g. Yes, so g is complex.
So what's the index of this vector?
What is the number of? So this has n sub k would be the number of Fourier modes, and n is the number of I values. So this would be nk times n is the length of that vector times 2 because of the real and imaginary parts. Okay, so this is just the probability. We've prepared an ensemble of systems, perhaps all having the same mean value of energy and our invariance g, but they might have random phases, for example, and we can then ask how do they evolve in time. And then, yeah, maybe just to be clear, over here g was a dependent variable, while over here I'm thinking of it as an independent variable. It's going to be a phase space. So if we integrate p over all possible values of g at the first value of k and the first velocity, and integrate over all possible values of g at the second value of k and the first velocity, etc., up to the number of k modes and the nth velocity of p of g, that's going to be equal to 1. Okay, so that's my normalization for this this phase space probability. Okay, so we have some high dimensional problem here, and for those of you who had a really good statistical mechanics course, this is all straightforward and trivial. But I wasn't blessed by such a course in college.
Who taught yours? Let's get it on the TV.
You actually can't blame anybody because I never took a stat mech course.
Ah!
I somehow managed to skip around that. Anyway, because the dynamics is conservative, we just have
us where you were educated, right?
Hmm?
Do you want to tell us where you were educated?
Sure, I can tell you.
MIT folks.
Yeah.
Up the river from MIT. So because the dynamics are continuous, if we know the state of a system at one instant of time, then we can evolve this equation to see what it would be like a little time later. And so there's a phase space conservation law like that. And the amazing thing is that, well, one amazing thing is that this commutes. There's a Liouville theorem that holds. So that's also true. So G dot is just this is just like we derive the Liouville equation or the Vlasov equation. And so G dot we can evaluate from here. And what we've got to prove in order to make this step is to show that phase space is incompressible, is to show that that's 0. And this is true because if we look at any individual component, I should be a little bit more careful. Let me make this a dot product. Okay. If we look at a given K mode and ask what is the rate at which G dot for that K mode changes as G dot is for that K mode is changed. The evolution of G sub K depends only on other modes P and Q that are not equal to K. Okay. If I was to set P equal to Q, I'm sorry, if I was to set P equal to K, then Q would be 0, and if Q is 0, this vanishes. Okay. So this turned out to be to satisfy phase space incompressibility. And now we can use a lot of the standard results of statistical mechanics. So P is constant along trajectories in phase space. And if we consider if the dynamics are sufficiently mixing, if an ergodic hypothesis holds, so that in some phase space, extended phase space of many parameters, if an ergodic hypothesis holds, then, and if we look at a limit where we don't care where we started on the trajectory, then all possible points on this are equally likely, and we can assume that P is constant. Now we have constraints on the problem, and we will be considering the case where all of our systems were prepared with certain energy. And so in that case, it would be kind of a hypersphere. It's kind of hard to draw. But we might wander around on the sphere, but we will conserve some invariant in that sphere. And so the microcanonical distribution would say that the energy, which depends on G, it's a functional G, is conserved, and so we will always lie on a hypersphere with a certain energy, and likewise there are other invariants times delta of G, Gi, which has some initial value, and in general we will multiply together all of these conserved quantities. So that would be the microcanonical ensemble. But as we know, when you have many degrees of freedom, it's simpler to work with the canonical ensemble, the Gibbs canonical ensemble. And the easy way to derive that is to say that we're going to maximize entropy subject to constraints that we satisfy the average values of E and G. And I'm not going to have, So, and the result, if we all recall, so we would maximize the phase space entropy, which in this case would be integral over phase space of P times log of P. And subject to constraints that there's a certain amount of energy and average values of those quadratic invariants. And the result that I will just assert is that this probability function becomes an exponential times a linear combination of the conserved quantities. E is a function of G plus the sum over all of our other GIs, which are also functionals of G.
We have to have lots more Ks than Vs in our discretization. If we had substantially fewer Ks than Vs, it seems like you'd over-constrain things.
I haven't thought of limits
Just thinking how many
of where those
constraints
limits
there are
there are.
here to
Ah,
size of vector.
uh-huh. Right.
So I have a constraint for every V, so if I just chose a discretization that had zillions of Vs and only a few Ks, I'd surely get into trouble.
At some point you might. Uh-huh. Where that might be, I'm not sure. Yeah. Okay, I need an eraser. Anybody see an
Use that
eraser?
sign that says please erase.
Huh, there's no eraser up here.
But there might be just outside.
People never make mistakes here.
Is there one where the
No,
chalk was?
everything you write remains there forever.
Down here. Okay. I've actually done all the hard parts. Now that we've done this, the rest is kind of grinding through some algebra with some interesting tricks. But let me just write this out. The first few steps, and then I'll try to show the results. So the energy is a functional of G up there, as are these invariants. And these are what you would get from these would be the Lagrange multipliers when you maximize the entropy subject to the constraints that you on average have a certain amount of energy of these invariants. So let me write out what those are. This is the exponential of minus, let's do this first. So I'm going to rearrange the order and do this first. It's going to be sum over all I, alpha sub I, times the sum over all k of g of k sub I squared plus alpha 0 times the energy, which is up there. I'm pulling out a factor 1/2, so I'll multiply that by 2, so I get 2 pi times the sum over k's of zeta of k times the sum over i's of wi, which can depend on k, times g of k I complex conjugate times the sum over j's of wj, which can depend on k, times g of k at j. And it all gets finished like that. Okay. And just a little bit of rearranging. This is an inner product, essentially. Which ones do I want to do first? Well, first I'm going to write this as an inner product. There's a k sum here and a k sum here. I'm going to pull out those k sums out front. And then I'm going to sum over all i's and all j's, the velocity grid points, times gki, complex conjugate here, times a bunch of things, times gkj. And to get this piece, I'm going to multiply by alpha I times delta ij. So when I sum over all j's, I just pick up the part where j is equal to I, and then that becomes that, with that there. Okay? And then here I just get plus alpha naught 2 pi beta of k times wi, which is a function of k, and wj, which is a function of k. Okay, so this whole thing can be written as the exponential of minus 1/2 sum over all k modes of, okay, now I'm going to introduce a little thing. So this whole thing I'm going to call a matrix, and I and j are the indices. So this is a matrix of in the velocity coordinates, I and j, but it's a function of k. Those two parameters are functions of k. Okay. And so here's a subtle, let's see, a subtle notational thing. Over here, vector g was a function, was indexed by both k and velocity space I. If I have a vector g with this k subscript, then I'm still indexing k explicitly, but I've written all of the velocity indices as a vector. Okay. And so this is in the form of a multivariable Gaussian, and so we can now work out the statistics straightforwardly. And this will be the inverse of the covariance matrix. And so in particular, if I ask what's the ensemble average of any quantity, it's equal to this covariance matrix, which is the inverse of whatever is here. Okay. And yeah, so we're essentially done. Now, this is, at first we wrote computer programs to invert this matrix, because it's in general a dense matrix. And we made plots of what the spectra look like. But it turns out that there's a trick for inverting this. Although it's dense, it has a special tensor product form, tensor product of one vector and another vector times a diagonal, which is easily inverted. And so one uses the Sherman-Morrison formula to invert that, which I learned from Michael Barnes and who learned it from Tomo Tatsuno. Right, so one can do that analytically, and then one can work out, eraser again. I guess for fun, I will use the other board over here, so looks like the camera's over here. One can work out the energy spectrum, which for subtle reasons we call D of k. Because this D of k is not the same as that E of k. We write this as k times D of k to absorb the, so this is just a 1D integral, while that's in general wave vector space. Okay, so D of k, which is going to be pi over beta of k times the ensemble average electrostatic potential. That's the conserved quantity. This can be written as pi times beta of k times the sum over all i's of these weight functions of k divided by alpha I divided by 1 plus alpha 0, 2 pi beta of k, sum over all i's, these weight functions of k divided by alpha I.
That's a simple question. How did beta go from the denominator to the numerator?
When you substitute for phi of k here, phi of k is this, so you get two powers of beta. Let me give you that. Okay. And these alpha i's and alpha zeros are what appear, they're the Lagrange multipliers here. And the way that they get determined is by, in our initial problem where we say initialize all of our perturbations in some place in wave number space, and you have to know the velocity distribution as well. Those will give you the initial values of these invariants. And we don't know how to analytically invert that, so we wrote a numerical root solver to adjust the alpha i's and alpha zeros to match the total energy and these other invariants, which we then have to sum this up over all k's. Okay.
This must be really tricky, right? Because some of the alphas can be negative,
Yep.
and you have a high dimensional parameter space here.
Yep.
It's even tricky in the standard case.
Right. Right. So is it possible that there are multiple solutions?
Well, not just well,
And
you never have trouble finding any solution.
Right. So you can So you can find solutions, and there are constraints. There are non-realizable values of E and D that are not compatible. But I've managed to, if you have a realizable initial condition, then I've always been able to find values of alpha 0 and alpha i's that solve it. My Newton root solver, since I'm here in this place, I used a Newton method to do the root solve. And it would often jump to unphysical values of alpha 0 that made this go negative. And so I had to constrain the root solver and often you were very close to the boundary between what's realizable and not. So you're right, this is a non-trivial problem.
How does realizability work with the ergodic idea? It seems like if some of the space that P was going to wander in can't ever be wandered in, then that messes up ergodicity.
Right.
Not necessarily. I mean, even when you talk about motion on the energy surface, right? That's the energy surface is really a constraint out of the whole phase space. So,
So we don't need total ergodicity. We just need it in some subspaces.
right.
Yeah. And hereby, it's realizability of these alpha 0s and alpha i's. They could give rise to negative values of D. I think most of the problem is well defined. Just for quick completeness, I'll write down. So G of I of K, you have to sum this over all K's to get the conserved energy, the total energy. And G of I, which is the ensemble average of G at a given K and a given velocity I, that is equal to 1 over 2 alpha I times 1 minus alpha 0, 2 pi beta of K, Wi squared, which can depend on K, divided by alpha I, all that divided by the same denominator, 1 plus alpha 0, 2 pi beta of K, sum over all L, WL squared. Okay. And so sum this over all K, sum this over all K. I have n plus 1, I have energy plus n constraints here, and that will determine my n values of alpha I and alpha 0. And then we can look at what spectra look like. So if you can lower the blackboard, lower the whiteboard and turn on the projector. He said it will take a minute for the projector to warm up.
Can I ask a question?
Uh-huh.
Can you show that if you start with a G where it's 0 above some velocity, that remains the case for that phenomenon?
I believe so. You would just set the alpha I is equal to infinity for that velocity. So it would then ensure that G is 0 above that velocity.
And is the G always a positive function when reconstructed, or has that been lost by going to this quadratic?
It needs to be positive, and that will be one of the physical realizability constraints on your choices of alpha i's and alpha 0s.
I meant the actual distribution function when you go back to X and Y space.
If you go back to real space, we're only dealing here with modes with a finite K. The K equals 0 mode never enters into any of the dynamics. You can always add enough of an offset so that the total distribution function is positive.
Well, the 0 component will be positive, but it could be that when you look at some particular point. That goes back to the issue of constraints.
Uh-huh.
Just take the quadratic. it's probably not significantly the same.
Yeah. You probably need, at high velocity, you need this to go to zero fast enough, and so alpha I has to get big fast enough for that to be satisfied. Okay. I'm just going to show a few examples. Where are we here?
Actually, I'm confused now based on
Okay.
Bill's question about ergodicity. There's some kind of an asymmetry between your K and your velocity of this problem, because the K's are convolved, and the V's aren't.
Right.
Which conceivably, I mean, does that, so these somehow, velocity structure isn't non-linearly interacting somehow in the
Right.
same way that the Fourier modes are.
Right. So, yeah, you're right. Velocity appears as just a parameter, and I'm essentially looking at just single points in velocity space. It's kind of like a delta function representation of velocity space. If I had used a real continuous basis, a basis that was continuous in velocity, then I would get convolutions in velocity. But because I'm using, I'm essentially, when I discretized, yeah, I was just looking at single points in V.
But let's explore that a little more. We know that there's some kind of free energy cascade, so that if we start with all the energy in a low order moment, that later we're going to get lots of energy in the high order moments. And so if we consider the GKIs to be moments, in, you know, some expansion where there are a bunch of basis polynomials to expand the G, then we are going to get, in finite amount of time, energy in the infinite alpha i's, or the GIK, so I'm confused. You can't make the alpha I big enough to beat that.
Right. There is a just like when you truncate in K space, you can only cascade up to your maximum K, and then there's nowhere else for the energy to go, and so it has to remain in your resolved modes. In velocity space, we have a certain highest Fourier transform of velocity space as well, and we're not allowing information to go up beyond that point. So this does contain correlations between one velocity and another velocity. Will be the inverse of this matrix, and you could look at how whether it's a delta. It's not exactly a delta function. If it was just this, it would be a delta function. Only one velocity is only correlated with itself, and you would. But there is some finite correlation between different velocities. So it doesn't.
Which is presumably how you reconcile that with the phase mixing cascade, right?
Okay. Let me just show you some sample spectra. Okay. So this particular case corresponded to initial value. I can't write it down. Let's see. I initially set g of x and v at time t equal to 0 to be cosine of k naught x times e to the minus v squared over 2 times j naught of k naught v.
K naught's just one in this plot, or?
K naught, for this case, I think I took k naught, which is really k naught rho I in Gyrokinetics, 0.3. So it was kind of on the longer side. So you can think of all the energy initially here, and then they'll let it relax. But it's with that initial distribution that I can calculate what these alpha i's are. And that initial distribution also determines this particular value of alpha 0. But I'm now going to vary that value of alpha 0 and see what different shapes I get. So just to point out that there are, you could get spectra that peak at high k, whereas alpha 0 becomes 0, that's here, and then as alpha 0 goes negative, it becomes peaked at long wavelengths. That's because of this over here. As alpha 0 goes negative, at low k, you get a near cancellation of this term with that term that enhances d at low k. Maybe more interesting are some of these.
What was tau of k in that picture?
1. Yeah. There we go. Okay. So this asks a slightly related question. With this initial condition, I now know all the invariants, and I can ask what's the equilibrium spectrum that it will relax to, and that's this curve. It really peaks at almost all the energies is in low k. And I compare that with Hasegawa-Mima for this same initial condition. Now, Hasegawa-Mima is the cold line limits. This is k perp rho s equal to 0.3. So you can see that they both give inverse cascade, and because it's a log scale, that point down there is almost identical, but Hasegawa-Mima does give a slightly more of a tail there. But if you were to follow this, if I was to extend k-space, this increases with k because the Bessel functions don't quite fall off as fast as you might have expected. Anyway, this is starting with k naught rho equal to 0.3. If I, let's look at figure 3. Here I've initialized the spectrum to be at k naught rho 5, 2, 3, 4, 5. So initially here, and Hasegawa-Mima will give some energy down here, but because it's so close to the border, you recall the Fjortov arguments that you can only inverse cascade energy if you're also forward cascading entropy. And because we're close to the border, there's a limit to how far we can forward cascade entropy. So Hasegawa-Mima for this case gives that spectrum, while the Gyrokinetic spectrum still gives a much stronger inverse cascade.
Are those the last 2 points for the, it looks like you have, if you're drawing a straight line between,
Yes, these are just 2 points. So, yeah.
You increased your domain size so that you have smaller k's. Would there always be a jump between the second smallest k?
Yes. Uh-huh.
So
Yeah. So this is doing real k sums. So there's a mode at k equal to 1, and
1D or 2D? Spacing looks 1D-ish.
yeah, this is I did this all not with integration approximations, but real sums over k's. And then I took all modes whose magnitude of k, the vector k had a magnitude less than that, and lumped them all in here. Yeah.
So that's that 0, that's one that's gone up so high?
This is k. This is the lowest k in the box. So this is the lowest wave number in the box. This is the second lowest wave number in the
In
box.
2D, does it tend to be all stripes one way, or is it, do you know?
If I set
Space information?
if I set tau equal to 1,
then you'll get all
then
the
it's isotropy. But if I do what ITG modes do, you greatly enhance zonal flows because the electrons don't shield them. So this is the case. This is an ETG-like case, or what Hasegawa-Mima originally did in neglecting the enhancement of zonal flows. Okay. So and then in this case, okay, this case is like this case. I initialize all the invariants from there, but then I added a background G squared. And so added this other invariant, well, that you can't see anymore, but this invariant, and arbitrarily enhanced that invariant while assuming the energy invariant was fixed. So it was adding an incoherent part to G of V that when you integrate overall velocity makes no impact on the fields, but does impact the value of the distribution function. That's kind of like adding noise in a pit code, kind of. Or in a continuum code, it's what happens when you run a continuum code for a long time and don't have enough dissipation. You will get a buildup of G squared from the entropy conservation laws. Anyway, that was our original spectrum. And enhancing G squared just by factor 4 causes a big jump up in the tail. But going another factor 10 only makes it go up a little bit higher. And you have to go up by a factor 500 before it finally becomes so big that it suppresses the long wavelength. So that's the overview. What are some interesting things for future work? I finished this and it's been submitted, and I'm going on to other things. But I think there are various areas for future work. One is that codes could test this. It would be interesting to do a comparison with the spectral code. Another would be to add magnetic fluctuations. You could look at what the spectra of the magnetic fields are. You can look at they're presumably going to be stochastic, and what's the nature of that stochastic field. How does that impact zonal flows? There is a thermal equilibrium zonal flow, but if you have stochastic fields, it's hard to have a shear flow with stochastic fields, and so how does that impact things? To extend this, I've done this in 2D. Here I've shown you just the 2D results, where it doesn't matter if you're delta F or full F. But our 3D results are only delta F. It would be interesting to extend it to full F and include the E-parallel nonlinearity. There's some subtle issues when you take a limit of delta V going to 0. And it might be interesting to try to think about that, but I'm not sure. I think ultimately you have to include collisions to have physically meaningful results. Just like we're truncating in wave number space, I'm not sure it's, what does it mean to consider an infinite number of Fourier modes? What's the impact of higher order Casimir invariance? If instead of just maximizing entropy with those two constraints, if you try to add higher constraints, what impact does it have? And then this can also be used not only as a benchmark for codes, but for statistical theories. If you're to try to do an EDQ&M or realizable Markovian closure for gyrokinetics or for the Vlasov equation, they should be able to reproduce spectra like this, and that would be an interesting thing to look at. Okay, I'll stop there. Thank you very much for your attention.